Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Today we teaching you how to calculate pH and pOH changes during an acid-base titration. So these are the concepts here that we're talking about. Show you how to calculate pH changes during acid-base titration, pOH changes during acid-base titration, and we talk about how core is derived from an acid-base titration, okay, between a strong acid and a strong base. But before we go into teaching you how to calculate the pH changes in an acid-base titration, we first of all look at how pH changes when a certain volume of a base of known concentration is added to a certain volume of acid of a known concentration. So this will give you some background knowledge that you will use when you do your calculations with regard to changes in pH during the titration reaction. So this is the problem here. What will be the final pH and pOH produced by mixing 300 milliliters of 0.1 mole per liter HCl with 200 milliliters of 0.1 mole per liter NaOH? This is how we go about doing that. So we are having a certain volume of HCl of known concentration. We can find the number of moles of HCl in that volume. So the first thing that you do is to find the number of moles of HCl by multiplying its concentration times its volume. So 300 milliliters translate into 0.300 liter, and that is the number of moles of HCl in that volume of solution. Then you want now to find the number of moles of hydrogen ions in the acid. Why we are doing that? We are doing this because it is the hydrogen ions in the acid that will be neutralized by the OH ions in the base that is added to it. So we want to know what is the original number of moles of hydrogen ions there. Of course, we know the mole ratio of hydrogen ions that is produced for every 1 mole of HCl that ionizes it, and it's a 1-to-1 mole ratio. I've spoken about this already, how you do that. That is the number of moles of the parent molecule, and you multiply that by the mole ratio there, which is 1-to-1. So we get this number of moles of hydrogen ions in that 300 milliliters of solution. Now we are pouring into that some sodium hydroxide. We're pouring into that 200 milliliters of sodium hydroxide that has this concentration, right? And of course that translates into 0.2 liters. I've done that for you already. So now you find the number of moles of sodium hydroxide that is coming in this quantity they bring in here. So that's the volume, that's the concentration, and multiply C times V, we get that for sodium hydroxide. But in there, you want to find one number of moles of that guy there. Do your mole ratio split there, okay, ionization, 1 mole to 1 mole. You take that as a paired compound, and you multiply by the mole ratio, 1-to-1 there, and we get that number of moles of hydroxyl ion. What happens when we mix hydrogen ions with hydroxyl ion? A neutralization reaction happens. So what is going to happen is that the H here, every H will be neutralized by 1 OH here. So 1 mole of hydrogen ions will be neutralized by 1 mole of OH ions to form a mole of water, and this is neutral. Okay, that's what it says, neutralization reaction. Let's see how many moles of that hydrogen that we had in the previous solution will be used up by that number of OH. See? Okay. So initially, we had that number of moles of hydrogen. Now we're adding that number of moles of OH. So when you do the math here, you find that if you minus this from that, you'll end up with this number of hydrogen that's left over. So in the solution, you're going to have an excess of that number of moles of hydrogen ions. So far, so good? All right. Two important things are to be made are these. There's a change in volume and there's a change in concentration of the acid. So far now, we've only been talking about number of moles of things that came in, and number of moles that have been neutralized, and the number of moles that are left in excess. So now what we need to do, we need to find the concentration of the hydrogen ions that are left in that volume of solution. Well, we want you to take note of this. Look. Initially, we had that number of moles of hydrogen ion in that volume. And now we're adding that number of moles of OH with this volume. Let's say I had a bigger container. And I took both of them and poured in this container here. What will happen is that, like we said before, this 0.02 mole of OH ion will neutralize exactly 0.0200 mole of hydrogen ions. And this new amount of hydrogen ion will be left in excess. All right, we did the math of that already. Okay, when we told that's what's left in excess there. But look, that amount is left in a bigger volume, and the bigger volume is the sum of this 200 milliliters and this 300 milliliters here. So these guys are floating around now in 500 milliliters of solution. To find the concentration now, we take that number of moles and divide it by a new volume, which is 0.500 liters. So take the remaining amount of hydrogen ions and divide it by the new volume, and you get this concentration here. That's a new concentration of the hydrogen ions. The number of moles in the original acid is this. When you add that number of moles of OH, it neutralizes the corresponding number of moles of hydrogen ion, and you're left with that amount there, okay? But now because you're adding that volume to that volume there, vice versa, you end up with a new volume of 0.5 liters here. So the new concentration of the leftover hydrogen ions will be equal to its amount in moles divided by the volume there, and you get this. Now that we know the concentration there, that can lead us to finding its pH. These are the very points we're making here, okay? That figure shows how that number of moles of hydrogen ions are neutralized by exactly that. And these are the leftover ions, number of moles, in this volume here, okay? Instead of 300. So go ahead now and find the concentration of this thing, which we did already in that cylinder here, as equal to this over this, and that's the new concentration. Now that we know the formula for pH, pH is equal to negative log of H plus ion concentration. This is the pH. Calculate the pOH. We know that pOH is equal to pKW minus pH, and this of course becomes the pOH. We will use the same principle here to find changes in pH during an acid-base titration reaction. Okay, questions are free to do. All right, these are found in the solution manual. Answers we stated to. All right, now we'll do changes in pH here. Right, watch this now. You want to calculate the change in pH that happens if you have 10 milliliters of 0.1 mole per liter hydrochloric acid when sequentially you add 2 milliliter portions of 0.1 mole per liter of NaOH. Okay? Okay. You want to find changes in pH. So this is what we have here. We are having an initial volume of HCl. This translates into that liters. That's my initial volume there, okay? So we know the mole ratio already. So you don't need to do all those things I show you to do. It's a monoprotic acid, is strong. So 0.1 mole per liter here, HCl, will give you 0.1 mole per liter of hydrogen ion. So the original pH of this solution here will be equal to negative log of 0.1, and the initial pH is 1. So hold that then, okay? So this guy has a pH inside here of, so pH is equal to 1. And the initial volume is this. So we're saying that because it's a strong acid, right? We'll assume that the number of moles of hydrochloric acid is equal to the number of moles of hydrogen inside here, right? So what we'll do now, we find the number of moles of H plus ion inside here. And N is equal to C times V. So this is equal to C, that's the concentration of the acid, times its volume here. And we end up with that number of moles of hydrogen ions, right? Now you find the number of moles of OH. Here we are seeing again, because it's a strong base, 1 mole of this will ionize to give you 1 mole of that, right? So number of moles of OH will be exactly equal to the number of moles of OH ions inside here, anyway. So the number of moles is found by, again, doing C times V. This is the concentration of the sodium hydroxide that you add in. And this is the volume, 2 milliliters. That's the volume in liters. So you're now adding that number of moles of OH to this number of moles of hydrogen ions. So what's going to happen? This number of moles will neutralize exactly the same number of moles here of hydrogen ions. So what we'll do, we'll take this guy and subtract that from it. Okay? So that's what we'll do. Excess hydrogen will be equal to what you had initially there, which is this, okay? Which is this. And you minus from that amount that you're adding there. And this is what you will be left with. So in this resulting solution now, watch this. You're going to have that amount of hydrogen ion now. But look what happens. Because to that now, you're adding 2 milliliters. The volume here will increase by 2 milliliters. So look, initially you had 10 milliliters, and you're adding 2 milliliters of your sodium hydroxide. So the final volume is equal to 12 milliliters that translate into that, okay? We know the final number of moles of hydrogen that's inside here, which is this. We don't do concentration is equal to N over V. This divided by a new volume here. And this is a new concentration of your hydrogen ion. You do a negative log of that and you get that. See, look, the pH went up. What was the pH? pH was 1. Why is the pH going up? The pH is going up because the concentration of your hydrogen ion is getting less because you're neutralizing it by OH. It's like this. Let me show you like this. Look, this is analogous to what is happening. Let's say you have 4 red balls in that volume of solution, right? And you're adding a blue ball, and every blue ball here is an OH ion, and every red ball here is a hydrogen ion. When you drop that inside there, this blue ball here will neutralize one of the red balls there to form water. So the blue ball and the red ball will disappear. So only thing you'll see are 3 red balls there. But this is bringing in a volume there. It's coming with a volume which is 2 milliliters. So the final volume will be equal to the initial volume there plus this volume that you're adding here. So this is exactly what is happening in this titration here. So here we are now. If you add another 2 milliliters, I'm going to do it. It's very painstaking, but As you continue to do this all the time, you'll see how these things are changing. You added another 2 milliliters. Now that has been added to this here, so that's going to become 14 now. These 2 milliliters of sodium hydroxide will add the same number of moles of OH ions as in the first case. Thus, we'll subtract this from what was left inside that solution. What was there initially? Initially, before we add this, that was there. See that? That was there in this solution here. We subtract again this from that. So now we left with a new amount of H in a new volume now. See, that was 12. Now we're adding 2. You end up with 14, which is this. So the new concentration will be equal to Cn over V, which is this one here, because we end up with a new amount, divided by the new volume here. And it gives you this. The negative log of that, again, it's 1.37. Why is it going up? You're taking out more of the H plus and you're adding some more volume. So therefore the concentration is changed. So again, now we're adding this again to a new volume with a different amount of H, which is this. So you subtract. So this is the amount you already calculated there. This is always the same number of moles of OH you're adding there. So take what you had before minus that. End up with new amount of H plus in a new volume now. They had 14 before. Now you're adding 2. You end up with 16. That's what it is in liters. So you take the new amount of hydrogen that is there, divide by new volume, which is equal to that negative log to 1.6. See? pH is going up again. Why? 2 reasons. You're removing some amount of H plus and you're adding more water there. Again, you add that translates into this. Then you subtract that from what was there before. You end up with that amount of new H plus in a newer volume now. Okay, it was 16 now. You're adding 2. Give 18, which is this, liters. Find a new concentration now. That is the amount that's left over. Okay, of H. Divide by a new volume there. Translate into that. Find your pH of that. And negative log of that gives you that. Again, same amount of OH is being added, that amount there. And you're going to minus that from the amount that you had before. You end up with 0 mole. Oh, in this case now, there's no excess mole of hydrogen here. See? At this point, all the excess hydrogen ions have been neutralized by OH ions. So there's no excess remaining hydrogen ions. The only source of hydrogen ions is from the auto-ionization of water. This is called equivalence point. And the amount of hydrogen there now on OH is what you have present in water. So what will happen in the solution? Now it's going to become basic. So let's see what's going on now. So that was the initial volume there. This is what happens when you add that there. It gives you this, it gives you this. Keep adding that amount there to the neutral mixture now. Of course, that is the number of moles of OH you're adding. Now you want to find excess OH. And that is the excess OH now. Find this new volume now. You have 20 milliliters. Now you're adding 2 milliliters to that. You get 22 milliliters. That's a new volume there. Find a new concentration of the excess OH. And this is the amount that you're adding there, new amount. So you take this that you added there and divide by a new volume. And that is what you get there for the concentration of the OH ions. OH ions, you want pH. You can use OH to get pH. You find pOH. Recall that this equation here, and that 14 is equal to Kw is equal to pH plus pOH. So pH will be equal to 14 minus pOH. So we can find the pOH of this solution here because we know the OH concentration, okay? pOH gives you this. The negative log of this will give you pOH. Then the new pH now will be equal to 14 minus your pOH. And see, it is 11.96. It's getting now basic. Alright, pH is going above 7. If you add another 2 milliliters, we always know that is the amount of OH you're adding. You don't have to keep calculating all the time. But it's being added to what is there before. That is the amount that was there before. Now you're adding the same amount there. Okay, so in the end, you end up with a new amount of OH, which is this. But in a new volume of 2 plus 22, that's equal to 24 milliliters in this. So you can find new concentration of the OH, N over V. N is this, right? V is this, new guy. And you end up with this. Do a pOH for that. pOH is equal to negative log of that. This is this. Subtract from 14, and you have a new pOH. So why don't you, as an exercise, you continue adding do a few more of that based on what I've done there for you there. Okay? And this is, if you plot those values there, you're going to get a pH curve like this. For a strong acid and a strong base, you get a line going up straight. This is equivalence point there when the pH was 7, right? And the moment you start to add little things more, see how the pH pushes itself high up like that, okay? We have a problem here. At pH 7, what will happen if you put 1 drop of sodium hydroxide of 0.1 mole per liter? See, a volume of 1 drop is approximately that milliliter, and that translates into that liter. We need to find the new pH after equivalence point is reached. At pH 7, we had 20 milliliters in that previous titration, okay? You want to know what will be effect of dropping 1 drop of that sodium hydroxide inside. So that is the number of liters of sodium hydroxide. Find the number of moles of OH ions inside here, first of all. You know, at pH 7, this is the concentration of OH ion as well as hydrogen ion. So we're more interested in OH ions. So the number of moles of OH ion in 20 milliliters at equivalence point will be equal to the concentration of OH in the solution times the volume there, which is this. So the total amount of OH ions that we have inside there at the equivalence point is equal to that. Now, what is the number of moles of OH that's added from 1 drop of that sodium hydroxide of this concentration? This is the concentration of this sodium hydroxide here, okay? And we are multiplying by the volume of the 1 drop here, and this is the amount of sodium hydroxide that 1 drop of it will have. So we are adding that to that amount. So this is the amount from the 1 drop, and that is the amount that was originally present at the equivalence point, and is approximately equal to this. That number of moles of OH. So C is equal to N over V. Take this and divide by, you're dividing by 20 milliliters because you're assuming that 1 drop is insignificant. It doesn't change this by much, right? It does not contribute. Look how small that 1 drop is, okay? Look at the volume of the 1 drop. Very, very small, right? Look. That volume of 1 drop is very, very small. Look. See? It's like 0.0005. See that? So it wouldn't contribute much. So the concentration of the OH will be equal to this value here divided by the volume of the solution, and this is what you get. So pOH now is equal to negative log of that. Subtract from 14. So look, the pH was 7, and that 1 drop is able to change it to 10.4. So don't underrate the value of 1 drop of sodium hydroxide. So that is how, man, you do changes in pH when you do an acid-base titration. So quick review of that. I'm not going to review the whole thing, it's a lot, right? So basically, if you understand this here, you understand everything. You will have a certain volume of an acid with a certain concentration, okay? You first of all find its initial concentration, the initial concentration of the 8 plus ions, and that will give you its initial pH. So you hold that. You then calculate the number of moles of H ions inside. In this case, we get this as the amount initially, okay? Then sequentially, you're adding 2 milliliters of 0.14 per liter NaOH. In that case, because they're all strong acids and strong bases, we're assuming the number of moles of OH corresponds to the number of moles of NaOH. So you just find the number of moles of the OH you're adding, and you subtract that from the initial amount of hydrogen that you have, and you'll get a new number of moles of hydrogen ions there. But because you're adding a volume, you end up with a new volume here, okay? New volume, and you find a new concentration by taking what's left here, all right, after you do your subtraction here, and you divide it by that, and then you find the log here. And it's like, what is happening here? You have a certain number of moles of hydrogen ion here, and you add some OH here that reacts with one of that. It disappears to form water. But when you do that, you're increasing the volume there. So a different number of moles with a different volume, you get a new concentration with a new pH. And if you do that sequentially, you don't think you're going to have any difficulty doing what you've done there. Has been very intriguing. I try my best to put all these different figures for you to see, to make it nice. I don't think you can find this anywhere. I hope that was helpful for you. If you don't want to do it at this level, you don't have to. But if you feel you can learn it now and learn it well, it will serve you in good stead when you do your grade 12 chemistry. So thank you for listening. Minor corrections, a little mistake I made here. I think but when we're finding the volume, 0 was missing here. I think 0 and 0 should be inside here, the part there, okay? This we should be having zeros. Is 0, another 0 should be inserted here, okay? Another 0 should be inserted here. Wherever we have those, right? Another 0 is supposed to be wherever we have these decimals here. Another 0 is supposed to be there. All right, 0 is supposed to be in front there. Didn't change the answer though, okay? Didn't change the answer. The answer is perfect. All these answers are right, but just as I made a little mistake with those zeros there, okay? So another 0 is supposed to be here, okay? Another 0 is supposed to be there. Well, the answer is right. The answer is right. All right. Okay, another 0 is supposed to be here. Answer is right. All right. Okay. Yes. Another 0 is supposed to be there, but the answers are perfect. All right. Well, thank you for that. Bye.